Alright, thus far in our exploration through axial deformations, we have looked at members that were subjected to a uniform axial force and had prismatic cross-sectional and geometric properties such as what you see here. And that was simple development of the model delta equals NL over AE. Then we looked at a situation that although the member was prismatic and had constant properties throughout, the axial force varied, and we handled that in this discrete way of working with things, but everything was all axial in nature. And now in this example, we're going to look at a bar that is supported partially by a flexible aluminum rod, and we have a load out here, and now we're going to ask what's going to go on. Now we're going to ignore the stiffness of this bar, A, B, C, D. Right? Flexurally, we're going to say it's rigid, even though in reality it probably is more flexible than the rod. You'll see why as we get on later into the semester about why I might make that kind of claim. But a lot of these that we work with here for small mechanical assemblies, like we might have here, 12 inches, 12 inches, 6 inches are these distances, so a total of course, 30 inches from. Ooh, that actually does make this fairly a stiff kind of bar, so maybe it's not so unrealistic. We'll see what happens as we go. But notice here the big difference is the force is not applied in a purely axial way on the member itself, although we have some pin connections going on, and that'll be important as we go along. We're going to have to do real structural analysis here is what this is going to amount to. We've got the aluminum having a modulus elasticity of 10,600 ksi, about 1/3 that of steel, a yield stress of 60 ksi, that's comparable or larger than a lot of steels would be, and we're asked to find what load can be applied at D. Well, that's different than before. Before we always said here is the load, but now we're at what load can be applied at D if the yield stress if the stress in the aluminum rod is no more than the yield stress. So in other words, we're saying let sigma in the aluminum be equal to its yield value, which is 60 ksi, and what's the P, the axial, or rather not the axial, but the force out at point D that would cause that to have that stress. And then we've got, well, how much does point D displace? Not deform, but displace. That point can't deform, but it can displace. How much does it go down? How much is delta D when this thing displaces? Now, when we say that the bar is rigid, that the axial elongation or the aluminum rod can deform, what we're saying is that the displaced shape of the structure is such that ABCD is still straight after displacement, after something deforms, in this case the little aluminum rod. Alright, so let's see how we're going to go about doing this. Now I'd like to make a big gigantic guess here, and my guess is that the force is 19.2 kips, and well, that's the answer that's provided to us. And so now anything I do to guess is not going to be quite as authentic. You're not going to believe that I'm truly guessing anymore. So we're not going to do that. We're just going to work the problem, see what we can learn, see how we can think about this for future kind of problems, so we can have more informed guesses before we see an answer. All right, so let's start with the free body diagram in the original position of the structure. All right, now you can tell if this 30 inches long, and if the answer really is correct that D goes down by 0.145 inches, there's no real significant difference in the geometry as this bar would rotate and go down a little bit. So that's probably a good way to understand that we're not going to worry about the deformed position of or displaced position of the system. Here's our force at D called P. We don't know what that is. We have a pin support here. We'll just put in AX and AY. We don't know what those are yet. With this displaced shape, we can see that the aluminum rod would elongate, so that means it's pulling back on the bar just as the bar is pulling down on the rod. So equal and opposite kinds of things. And so that's your axial force in the aluminum. Right? And from that, note that, okay, well this is basic statics. There's a direct relationship here between the aluminum force is 12 inches away from A and the applied force is 30 inches away. Now note, NAL is a lot closer to this pivot point than what P is, so it's going to be a lot bigger than what P is at basic statics. We come along some moments about point A. Let's take counterclockwise positive. We get 12 times NAL minus 30 times P, and of course it's static equilibrium, so we'll set that equal to 0, and we find out then that P will be equal to 12 over 30 times the force in the aluminum rod. Right, now we're trying to find P, so that's why I solved it this way, and we're in a condition that says that the axial stress is a specific value in, oh hey, axial stress and axial force are going to be related by sigma equals N over A. Right? Oh, alright, well that tells us also that then N is equal to sigma times A. And since we know what sigma is, we can go after it. That NAL will be equal to sigma AL times the area of that member, and that stress is 60 KSI, and so the way the problem is set up, times the cross-sectional area, which we're told is 0.8 square inches, so kips per square inch times inches squared will give us a force in kips, and 60 times 0.8 is 48. So under the conditions of analysis, then our axial force in the aluminum is 48. And now we can go find our P, because it's equal to 12 over 30 times our force in the aluminum, and that is then 12 over 30 times 48 kips. Notice the inch over inch was canceled out already, and so 12 divided by 30 times 48 is 19.2. In positive indicates that's going in the direction that we had indicated. It's going downwards, and so there's our answer for that. Right, now let's go figure out how we're going to get the displacement. Let's do a slightly magnified version of our system that we had on the previous page. That is, there's our reference position, the undisplaced, undeformed position. And now let's draw this out a little bit further. Remember, now answer again is really small, and so even though bar A, B, C, D, this tip D cannot move directly down, it'll have to rotate if the bar is really rigid, doesn't flex, but it's so small is our hypothesis. There's our delta sub D, that we're going to say, no, that we're going to create a little right triangle here, and we're going to say that that's moving straight down. I know it actually moves in an arc, but trust me, I work for the government. It's going to be okay. We may have been introduced a little tiny amount of error, but it'll be okay. Right, and there's your delta B, the displacement at B. B is 12 inches away from A, which doesn't do anything except for rotate, and then of course we've got another 18 inches on out from there to there, a total of 30. And by similar triangles, then note delta B is to delta D as 12 inches is to 30 inches. And so now, since we want delta D, right, then delta D is 30 over 12 times delta B. Note, this is the exact opposite of what happened with those forces in this particular one. That the force out here at D was smaller than the force at B because of the equilibrium, but now the displacements are reversed in their ratio. Right? And so now all we have to do is find out, well, what's the displacement at B? Well, that's happening entirely because of the flexibility of our aluminum rod. So since the top end of the rod doesn't move, that means delta B is going to be equal exactly to the deformation, right? Displacement at B is equal to the deformation, in this case of the aluminum rod, in a model for a centrically loaded prismatic member with constant cross-sectional force and properties is that that's NL over AE for that member. Right? Now, we actually already know what the stress is. That was a N over A is that stress, so that's 60 KSI. Right? The length of the rod, we're told in part, the second part, is 10 inches long. We already have the cross-sectional area, that's 60 KSI over the N over A, and we've got then the E, which is 10,600 KSI. KSI over KSI means we're going to get the length units as our number, and that will be equal to 0.0566 inches. Not very much at all, right? And then that gets magnified here, 30 over 12 times 0.0566, and then, well, I sure hope this equals, oh, it does, 0.1415 inches going downwards, and that's an absurd level of significant digits. We should call that 0.14 inches to the hundredth. To write it out to the 10,000ths is just absolutely absurd. We don't have that kind of precision in any of the work that we're doing here. Mathematically, yes, but not in the actual measurement of anything. Right now, I want you to have one more perspective about what's really going on here, and that is that we isolated the flexibility in the system entirely to the aluminum rod that was connected here at B. We could think about that as a little coil spring with a little constant K. That's where all the flexibility in the system was located. Right? And that's a pretty useful way of looking at this. Means that we've, of course, looked at the bar as being rigid. And you say, well, okay, so what's that value of K? K is that relationship, remember, F equals KX. The physicists say, I don't like that. It's really axial force equals K times the axial deformation that's happening. And we know that that model is EA over L times delta. This EA over L is our axial stiffness. And in computer models, that's exactly, not approximately, not an analogy, it is exactly what happens in our computer modeling. Right? And so here, let's just get a sense of the scale of this. EA over L for this rod, we got the E at 10,600 kips per square inch. We have 0.8 square inches of area over the length of only 10 inches. And this number is going to be pretty gigantic. It's going to be 848 kips per inch. You say, well, 848 is not a big number. Whoa, 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 whoa. Note the units. Kips, 848,000 pounds per inch. It takes 848,000 pounds to elongate this 10-inch rod by 1 inch. Holy schmoly, that's a lot of force. Right? You're only going to see that at the bottom of really tall buildings or platforms out in the ocean. 848,000 pounds to get an inch of deformation in this particular very short length of a rod. That's extremely stiff, right? And that's common for axial kinds of situations. Now, one last final thing I want to nail down, right? This is all just value added as we're looking at this problem. And that is, let's go back, 0.1415 inches. And I said, hey, don't worry about how D moves down. It does, yeah, okay, it arcs. No, it's just make an approximation here. But hey, look at this. Let's find out what this angle theta is. Okay, tangent of theta is equal to opposite over adjacent. That'd be 0.1415 over the 30 inches. Right? And theta is going to turn out to be a really tiny number, 0.1415 divided by 30, inverse tangent, and that's 0.27 degrees. Alright, so if you want to try to go find out how much D actually moves to the left, you knock yourself out. It's going to be a total waste of time. Right, that's going to swing over as an arc, and then we'll project it back. So now the hypotenuse is 30 inches. So we'll take, now it'll be, let's see, cosine of that times 30. That's how much. All right, so that's the length projection on there minus the 30 inches. Get rid of the minus sign. Okay, delta D in the x direction is approximately 3.3 times 10 to the minus 4th inches to the left. Again, knock yourself out if you want to deal with a more complicated, oh, it swings like an arc, but we're talking about 3/10,000ths of an inch to the left compared to a little more than 1/10 of an inch moving downwards. Ignore this in real structures until, of course, it does matter, and you have to have sense of when that might be. Not very often will that actually matter.